Hi, Chris Good here with another video. We're going to do an analysis of variance, and we're going to use the data from the Mozart effect study, the simplified data that we've been discussing in class. So these are going to be a little bit easier to work with than the numbers from the original study, and not quite as many of them either. And since there are three means, and we're looking for an overall effective treatment, right, is one of these means different from at least one other one, we're going to do an analysis of variance, which is a hypothesis testing statistic. So the step number one is going to be, actually I'm going to write it down here, step number one is going to be to state that null hypothesis. So the null hypothesis always is the assumption that your treatment has no effect, and in this case we're going to assume that whatever you listen to doesn't have an effect on your IQ score, which means that these means, right, these sample means, might as well have come from populations whose means were equal. So the mean in the population of IQ score of people after they listened to Mozart, right, should be equal to the mean after they listen to a relaxation tape, and they should all be equal to the mean after they don't listen to anything at all, after they listen to silence. That's our null hypothesis. Step number two is to set your alpha. We're going to choose a nice one like 0.05, and to find the critical region. And the critical value for f is going to be dependent on not one, but 2 degrees of freedom. And those degrees of freedom are in the numerator of your f ratio, right, and the denominator of your f ratio. Now, f eventually is going to be equal to the variance between your treatments divided by the variance within your treatments, and I'm abbreviating there. But so we're looking essentially at the variance of these three numbers here divided by the average variance with for each one of these three distributions of numbers. The variance here, averaged with the variance here, averaged with the variance here. So we need to find how many means we have, 1, 2, 3, the average of all these three means, right, which we're going to use as an estimate of the overall population mean, essentially. When we do that, every time you estimate a population parameter, you lose a degree of freedom. We have 3 means here. We're going to lose 1 degree of freedom, so that's 3 minus 1 is equal to 2. So k is a useful number. That means the number of groups that you have. We have 3 groups. The degrees of freedom associated with the numerator term, then, the degrees of freedom between treatments, is always going to be equal to the number of groups you have minus 1. The number of means that you are comparing minus 1. In this case, it's 3 minus 1, or 2. We're going to contrast that with the degrees of freedom in the denominator. The variance within treatments, within each group, is what we're looking for. You have 5 scores in each group. In order to create this mean of 4.8, we could have 4 of these scores have any value whatsoever. The 5th value would be fixed for this particular mean, and so we lose 1 degree of freedom there. Therefore, the degrees of freedom... Oh, but we also do the same thing here and here. There's 15 total scores, so I'm going to use big N to represent the total scores. And you'll find that if you subtract 1 from each treatment, so subtract 1 score, you end up with all of the scores minus the number of groups that you have. Subtract 1, 2, 3 groups from the total number of scores. So the degrees of freedom within treatments is equal to the number of scores that you have minus the number of total scores you have minus the number of total groups that you have, or 15 minus 3 is equal to 12. Okay, so now we have the information that we need to look up the critical value for f, that for 2 and 12 degrees of freedom, and I'm going to do that on the computer. I don't have my table handy, but, well, here, you can share my screen with me. There we are. So this is the F distribution. It's from your textbook, table B4. And you'll see that across the top we have degrees of freedom in the numerator, and down these rows, we have the degrees of freedom in the denominator. We decided that in the numerator there were 2 degrees of freedom because we had 3 groups. And you'll notice that table entries in light face type are critical values for the 0.05 level of significance, so we need to use the light face type. In the denominator, we decided we had n 15 total scores, minus 3 groups, k, equal to 12 degrees of freedom. So 2 degrees of freedom in the numerator, 12 degrees of freedom in the denominator. Our critical value for f is 3.88. Great. All right. Remember, the statistic we're calculating is essentially the variance. It's a ratio of one variance to another. In order to do variance, you need sums of squares. Well, let's do the sums of squares that we've already know about. So, sum of squares for the numerator is going to be the sum of squares within treatments. That's essentially the sum of the sums of squares for each treatment. It's just the sum of the square deviations of each one of these scores from their mean, plus the sum of the squared deviations of each one of these scores from their mean, plus, you guessed it, the sum of the squared deviations of each one of these scores from their mean. Okay? Oh, that's just a duplicate there. Let me get some scratch paper out, and here we go. I'll tell you what, let's do the sum of the squares for the Mozart group first. So, sum of squares for Mozart is the sum of the squared Mozart scores minus the square of the sum of their scores divided by the number of those scores. That's 25 plus 49. I'm just squaring the Mozart scores here. Plus 16, plus 16, plus 16, minus the total of all the scores, which I've actually calculated these. We call those the T's. So the T's are the totals within each group. T here is 24 squared over the number of scores, which was 5. Let's go ahead and add those up. 25 and 49 and 16 and 16 and 16. Oops. I'll try that one more time. And I get 122. 24 squared is 576. Divide that by 5, and we get 115.2. Or 6.8. So what I'm going to do is copy that value down on our chart here. For the sum of the squares, I got 6.8 for the Mozart group. Let's do the same thing for the relaxation. That's the sum of all the relaxation scores minus the square of their sum divided by the number of relaxation scores we have. And I'm just going to square each one of these scores. So 4 squared is 16, 6 squared is 36, 9, 4, and 9 minus the total number of scores we have there, 18 squared, over the number of scores, which is still 5. So that's 16, 36, 9, 4, and 9, or 74, minus 18 squared, which is 324, over 5, which is 64.8. I get 9.2, right? That's my sum of squares there. I'll fill that in the table. Finally, for silence, I get the sum of the squared scores minus the square of the sum divided by n is 4, 25, 9, 1, and 4, minus the total, 13, squared over the number of scores, which is 5. So 4, 25, 9, 1, and 4 is 43. 13 squared is 169. Oops. Right? 169 divided by 5 is, that's minus 33.8. That should be 9.2 as well. So I'm going to squeeze this in down here. That's 9.2. And all we have to do is add up these sums of squares. That's 6.8 plus 9.2 plus 9.2. I get 25.2. So 25.2 is our total sums of squares, and that's the sum of squares within all of the treatments together. Just double check that, man. Yep, 25.2. So this is going to be the sum of squares for the denominator. It's not the variance, it is the sum of squares. We're going to, well, actually, you know what? What would the variance be? Variance is always equal to the sum of squares divided by the degrees of freedom. We're actually going to calculate something that's not technically the variance. We call it the mean square, or the mean squared deviation. But it does have the same formula. The mean squared for within treatments is equal to the sum of squares within treatments divided by the degrees of freedom within treatments. So that's 25.2. The degrees of freedom we calculated earlier, it's the number of total scores we have minus the number of groups, or 12. So 25.2 divided by 12 is 2.1. And that's going to be what we use in the denominator of the F ratio. It essentially is the average variance within each one of these distributions. What goes in the numerator then? Well, it's the sum of squares between treatments. And this is a new formula. It's the sum of the squared totals divided by n for each group. That's this squared total, but divided by the number of scores we have, plus this squared total divided by the number of scores we have, plus this one divided by, and you subtract from that the g squared. G, remember, is the total of all of the scores. 55 is all of these 15 scores added together. And we divide that by the total number of scores that we have. So what would this look like for this group of numbers? Well, that's 24 squared over 5. Remember, I'm just squaring the totals, dividing by the number of scores in each group, plus 18 squared, I've got that here from this total, over 5, plus 13 squared over 5, minus 55 squared over 15. So 24 squared then is 576, that's divided by 5. 18 squared is 324, divide that by 5. 13 squared is 169, divide that by 5. And 55 squared, remember we're subtracting this one, is 3025, divided by 15. So 576 over 5 is 115.2. 324 over 5 is 64.8. 169 over 5 is 33.8. We're going to subtract 3025 divided by, not 5, but 15. And that's, sorry, let me do that once more time. It's 3025 divided by 15, which is 201.67. All right, let's do the math. 115.2 and 64.8 and 33.8 is 213.8 minus 201.67. That's with rounding. And I get 12.13 for my sum of squares between treatments. Make a little more room here. So if variance is equal to the sum of squares over degrees of freedom, then the variance for the between treatments term, which we're going to call the mean squared between treatments, is equal to the sum of squares between treatments over the degrees of freedom between treatments, which we calculated up here. It's the number of groups that you have minus 1. We're interested in the variance among these 3 groups. So that was 2. So 12.13 over 2 is 6.07 with rounding. And that's going to form the numerator of our F ratio, which is the mean squared, which is kind of like variance, mean squared between treatments over the mean squared within treatments. Or, let's copy this from up here. That's in the denominator. 6.07 was our between, 2.1 was our within, and I get 2.89. Sorry, 8, 9. And that's with a little bit of rounding fudged in there because I did not round up 6.07 before dividing that. So if you do that the other way, 6.07 divided by 2.1, it's still 2.89. Alright, that's our calculated value for F. We have our critical value for F right here is 3.88. And what I want to do is bring back that F distribution, just the plot of it that's from your book. The critical value for F was 3.88, and our calculated value was less than that, so it's in the body. It's not in the shaded region, so we're not going to reject the null. We're going to fail to reject, and we'll conclude that there is not a significant effect of treatment. We detect no significant difference anywhere among these 3 means. Even though people had a higher IQ after listening to Mozart, it's not significantly higher than the IQ after listening to the other things, the other conditions of the study. So, we'll fail to reject. That's step number 4. That was step number 3 down here. And we'll conclude that we did not detect a significant effect, that's with an E, of listening condition, that's our independent variable, on IQ, with F of 2 and 12 degrees of freedom equal to 2.89, and a probability here, assuming the null hypothesis is true, of greater than 0.05. And that's the end of our sentence, and that's the end of this problem.